Okay, so here's an example of a first order kinetics problem. So just consider a reaction that has first order kinetics. Sometimes the question will tell you what order the reaction is. Sometimes you have to use some information in the question so that you can know what order the reaction is in. In this example, the first order reaction is given to us. The half-life is 15.6 minutes. So notice the half-life is given to us in minutes, not seconds. So that means in 15.6 minutes, the concentration, the original concentration, is cut in half. Find the time required for the reaction to be 80% complete. So notice they're giving us a percentage or a ratio. The reaction is 80% complete. Be careful here. That means that there's 20% remaining. 20% of reactant remaining. So let's go find the time. Let's go to our first order kinetics equation, first order integrated rate law. And we're looking for the time required. So I'm going to divide both sides by negative k. So you notice, in order to solve the problem, we need to know the rate constant, which we don't know. So we need to go find the rate constant first. So let's do that first. The half-life is equal to 0.693 over k. If we rearrange this equation to get k by itself, k is equal to 0.693 over the half-life. 0.693 over 15.6 minutes is equal to 0.0444 inverse minutes. Remember, minutes is in the denominator. Okay, so now we can just plug this in. We can plug this number in here and solve for the time. So let's rewrite our problem right here. ln of a over a naught. Now we're 80% complete. That means there's 20% remaining. And so, as I mentioned in the previous video, the good thing about using these ratios is that if we're dealing with percentages, you know, I don't need to know exactly what the initial concentration is. All I need to know is, well, there's 20% remaining. That's the same thing as 20 over 100 divided by negative 0.0444 inverse minute. So I'll put over minutes. Minutes, of course, goes up to the top, is equal to t. So in your calculator, let me show you how to do this. In your calculator, we're actually going to plug in the natural log of 20 over 100 and divide it by negative 0.0444. So it looks like it takes about 36 minutes for the reaction to be 80% complete. Let me give you just a second part to this. let's find the concentration of A after, I don't know, we'll just say 20 minutes. If the initial concentration is 2.0 mole per liter. So a little bit different question. We know the initial concentration. We know, we want to know after 20 minutes, what is A going to be? What is the concentration going to be? So let's set up our first order integrated rate law. And we're looking for A. So a couple things we should do here. Plug in our data. Now we're looking for A. We don't know what that is. The initial concentration is 2.0 mole per liter. I'll put molarity for right now, is equal to negative K. Now we found the rate constant earlier, so that's this number right here. So negative, because of my equation, 0.0444 inverse minute times T. Now, in the question that I'm giving you, I'm telling you, well, I want to know the concentration after 20 minutes. Now, right here, you can see those units multiplying K and T, minutes and inverse minutes will cancel. So remember, when we're working with natural logs, inside the natural log is A. That's what I want to get to. So to get rid of the natural log, I'm going to say e raised to the natural log. E raised to this number right here. So this cancels. So A naught over 2.0 molar is equal to E raised to the, let me get that number for you, negative 0.888. So A, if we multiply this over, 2.0 molar times e to the negative 0.888. So in your calculators, remember to get to that e function, that's the second natural log, e raised to the negative 0.888. And so the answer we get here, 0.823 molar.